this Washington, D.C. hotel was the site of the infamous 1972 Watergate break-in. What is the Watergate Hotel? That sort of thing. Or this former U.S. president is buried in Grant's tomb. Who is Ulysses S. Grant? That type thing, where the answer is there. These rules, this first set of rules for logarithms, resemble, in my mind, these types of Jeopardy clues from the category stupid answers. So I'll refer to these as the Jeopardy stupid answers rules of logarithms. So they go something like this, and we'll look at them. Those in the first row are what happen when you evaluate an exponential function, get an answer, and then follow it up by evaluating the logarithm to the same base. And then the second row is when you begin by taking a positive number, evaluating a logarithm, and then following that up with the exponential function to the same base. So let's start off with, well, let's see, I guess I could take a picture of this and simplify it just a bit. And then give some examples. For any real number x, this one right here, if I start with x and then raise a to that power, no telling what I get. X could be positive, x could be negative, x could be any real number, and we can raise a to that power. We're going to get an answer, and then we're going to follow it by evaluating the logarithm. Now let's pause for a moment and think what the logarithm really means. A logarithm was defined to be an exponent. That's really the best way to think about a log. The logarithm is the power that the base a can be raised to get the argument as the answer. So if I want to get a to the x power as the answer, what power should a be raised to give me that as the answer? A should be raised to the x power if I want to get a to the x power as the answer. Let's look at a specific case for base 10 logarithms. If it's base 10 logarithm, it's invisible 10 right there for common logarithms, base 10 logarithms. If the 10 is not written, it's understood to be 10, or if the base is not written, it's understood to be 10. So consider this. Take 10 and raise it to a power. What's supposed to happen is that when we evaluate the logarithm, it gives us that power right back. Now let's think, what is 10 to the 6th power? Log base 10 of 10 to the 6th power. Well, 10 to the 6th power is a 1 followed by 6 zeros, like that. This is a log of a million. If I want to know what the base 10 logarithm of a million is, I try to ask myself, well, what power can 10 be raised to get 1 million as the answer? What do you think? 6. There we go. So log base 10 of 10 to the 6th power is 6. The exponential function takes that 6 and gives us a great big number, and the logarithm tells us the exponent, the original exponent that the base would have to be raised to give us that great big number. So it gives us the exponent back, in other words. And for the natural logarithm and the natural base, ln of e of x literally means log base e of e to the x. Excuse me. So I'm wondering what power e can be raised to get e to the x as the answer. It's going to be x. So that's just another way of saying the natural log of e to the x equals x. When solving exponential equations, at least one exponential equation that we'll run into in section 4.5, when we have a situation e to the unknown power equals a number, what we'll do is we'll take the natural log of both sides. And we'll say natural log of e to that power is just the power. And that will take care of the exponential, the natural base there. Reverse the process. Start off by taking a logarithm and then raise a to the appropriate power. Let's see, this one right here. If I begin with x, now in this case, x has to be positive because logarithms are only defined for positive numbers. We can't take the log of 0. We don't want to take the log of anything negative because that would be an imaginary number. We want to keep our logarithms real valued. So let x be positive and find log base a of x. Now this will give us the power that a can be raised to get x as the answer. That's what it tells us. So suppose we get the power that a can be raised to get x as the answer, and we raise a to that power. We get x as the answer. Just like that. So a raised to the power of a, which produces x. And we can do this kind of in reverse for the base 10 logarithm with the 6. Suppose we start out with 1,000,000. 1, 0, 0, 0, 0, 0, 0. And we evaluate the base 10 log of that. And then we take 10 and raise it to that power. So what power can 10 be raised to get 1,000,000 as the answer? 6. So this is really 10 to the 6th power. But wait, what's 10 to the 6th power? 1,000,000. So we start with 1,000,000, evaluate the logarithm, and it gives us 6. Then we evaluate the exponential function with base 10, and it gives us back the 1,000,000. So that's
the reverse of the original.
Right. And that's a good way to think about it. Reverse, inverse, something like that. If you do the logarithm first and then the exponential function, it gives you back what you started. These functions are inverses of each other. Now, the next few should be fairly simple if we use these properties. When we say log base 3 of 3 to the 10th power, we're wondering what power can 3 be raised to get 3 to the 10th power is the answer. Think of 10. Now the next one, even though it's base 10 logarithm, the TI-83s and 84s are not equipped to handle it because this would involve a 201-digit number. 10 to the 200th power is a 1 followed by 200 zeros, and that would produce an overflow error if you just punch it in. But it's easy enough. What power can this invisible 10 be raised to get 10 to the 200th power is the answer? 200. Just like that. And then it works if there's an unknown in the exponent. The natural log and the natural base are inverses of each other. Natural log of e to the negative 2.2t equals what? Just like that. Now I'm going to throw in an extra step with the d part here. Log base 3 of 243. We don't have to know what log base 3 of 243 is to know that the answer to this is going to be 243. But it's a nice power of 3. 243 is 3 times 3 is 9, times 3 is 27, times 3 is 81, and 81 times 3 is 243. So, what power can 3 be raised to get 243 as the answer? 5. So 3 to the 5th power. What's 3 to the 5th power? 243, yeah. So we don't have to do the middle step to know it's going to be 243. You put a 244 there, 245. It's going to be 5 point something. It's not going to be nice like 5 is, but the final answer is going to be 243. For this next one, we need to make sure that x is greater than 0. I didn't put the little disclaimer there, but let's say it is x is greater than 0. If so, we can take the log of 3x, and then if we follow that up by raising that 10 to that power, what do we get? Well, whatever we originally took the log of, we get 3x. And then e to the power of the natural log of 2k squared plus 3 equals 2k squared plus 3. Take the logarithm, follow it up with the exponential function, and get back the original. So we'll run into these properties again, and I'll refer back to them as the Jeopardy! Stupid Answer properties of logarithms. The others are the ones that were primarily the basis of the reading quiz. They have to do with taking a logarithmic expression, the sum or difference of logarithms, and combining logarithms into a single logarithm, or the opposite direction, if you have a logarithm of something kind of complicated, and you'd rather have logarithms of something kind of simpler than that, then you can expand the logarithms, and the price you pay is you have more logarithms to deal with, but what you get in exchange is the arguments of the logarithms, expressions you're taking the logarithms of, are simpler, easier to deal with, easier to handle. And depending on the situation, you might need to go one direction or the other. So let's look at these rules for expanding and condensing logarithms, and I'll see if I can provide some examples of these as well. Properties of exponents. Hopefully these properties of exponents are familiar. If I have a to the third power, and I multiply that by a to the second power, then I get a to what power? A to the fifth power. You have 3 factors of a, and then shove that up next to 2 more factors of a, and we have a total 5 factors of a. So we add the exponents when we're multiplying the exponential expressions there. There is a corresponding property of logarithms that if we have the log of a product, this is equal to the sum of the logs of those individual expressions. The log of m times n equals the log of m plus the log of n. So suppose we have log base a of 32. Just making up the 32. Log base a of 32. This is equal to log base a of 4 plus log base a of blank. What goes in the blank? Is it 28 or 8?
8.
Is it 8? Because what we want is to be able to say this: the log of 4 times 8 is equal to the log of 4 plus the log of 8. So we're multiplying the expressions here, but we're adding the logarithms. Now, in general, if we don't know the value of a, then we cannot evaluate these logarithms, but for certain particularly nice values of a, it's not too tough. For example, suppose we look at log base 2 of 32, and log base 2 of 4, and log base 2 of 8. Doesn't matter what base we use, we just have to be consistent, use the same base all the way across. So I'm just going to pick 2 as an example. We did at least 2 out of 3, maybe all these last time. What power can 2 be raised to get 32 is the answer? 2 to the what power equals 32? 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 equals 32. 5 factors of 2 there. How many factors of 2 do we have in that 4?
1.
Well, 2 times 2? Yeah. And how many factors of 2 do we have in that 8?
3.
3. So in much the same way, if you think of logarithms as exponents, what we actually do is adding the exponents, 2 plus 3 to get 5, just like we would add these exponents if we had, well, put it like this: 2 to the second power times 2 to the third power equals 2 to the fifth power. We're adding those exponents because 4 times 8 equals 32. What the logarithm does is tell you how many factors of that base you have in the argument. All right, log of a quotient equals the difference of the logs. This corresponds to the property a to the u, and let's go with something. How about this? 2 to the fifth power divided by 2 to the third power equals what? What do we do with the exponents when we're dividing?
Subtract.
You subtract. It's 2 to the third power, right? 5 minus 3 is not 3. 5 minus 3 is what?
2.
2. There we go. That's better. So 2 to the fifth divided by 2 to the third is 2 to the second power when we subtract the exponents. We can rearrange these and write it as a subtraction. How about this? Log base, let's go and go with log base 2 of 4 equals log base 2 of 32 minus log base 2 of blank. Is it 8 again? Because 4 can be written as 32 divided by 8. If you take 4 and write it as 32 divided by 8, then that's the log of 32 minus the log of 8. Now if I put the 4 back in, like that, we know log base 2 of 4 equals 2, and log base 2 of 32 equals 5, and log base 2 of 8 equals 3. So if you think of logarithms as exponents, which you should, we're subtracting exponents. 5 minus 3 equals 2, just like 5 minus 3 equals 2 right there. And the last one,
And you don't get the same answer.
what answers are different?
Well, like your exponent adding and subtracting,
Mhm.
and you have your 8. That's not the same.
Well, all I'm saying is that here we get 5 minus 3 equals 2, and here we have 5 minus 3 equals 2. We're subtracting the logarithms, not subtracting the arguments of the logarithms. We're not saying 32 minus 8. Final property, and the third on this list, log base a of m to the r power equals r times log base a of m. Now this works whether or not r is a whole number, but I think it's real easy to illustrate if we use an example where r actually is a whole number. Let me give myself a little bit of room to do this. Suppose we say log base 2 of 4 cubed. I'd like to be able to take that 3 and bring it out in front and say that's 3 times log base 2 of 4. Well, 4 cubed is 4 times 4 times 4. So this equals log base 2 of 4 times 4 times 4. Now I'm going to take a little bit of, license or freedom here and say that log of a product m times n can be extended to as many factors as we want. M times n times p times q times r. The log of a product of finitely many factors is equal to the sum of those individual logarithms. So this is log base 2 of 4 plus log base 2 of 4 plus log base 2 of 4, and then there are 3 of them. 3 times log base 2 of 4. Couldn't do that if the value of r is not a whole number. It still works if r is not a whole number. It's just not as easy to see exactly how it works. So 3 very important properties of logarithms, and we'll illustrate these in the next 4 or perhaps 6 examples. If we are, I guess I should come back and say one more thing here. If we're using the properties in this direction, going from the log, a single logarithm of a complicated expression to multiple logarithms of simpler expressions, then we are expanding the logarithm. On the other hand, if we use these properties in this direction, have multiple logarithms, and we want to condense them into a single logarithm, we'll call that condensing.
Note for next semester, more room underneath that.
More room. A lot more space there is necessary. Example 2, the A part and the B part have been done for us. So I will copy the directions. And also, let's look then at the C part and the D part. So it's on the next page. Is write each expression in terms of the log of x, log of y, log of z. Assume all variables are positive. It might be important to make mention of what we would do in the case where y could possibly be negative, but assume all variables are positive, and then we don't have to worry about that scenario. All logarithms are base 10 logarithms in this example because the bases are not written, and when they're not written, they're understood to be 10. So log of xy squared want to characterize the argument of that logarithm as one of three things. I want to characterize it as being either the log of a product, something times something, or the log of a quotient, something divided by something, or the log of a single expression raised to a power. So a product, a quotient, or a single expression raised to a power.
So the first one?
It's going to be the first one. It's going to be the first. It's the log of a product. Y is raised to a power, but x is not raised to the same power, so it wouldn't be good to call it a single expression raised to a power. No fraction here, so it wouldn't be good to call it a quotient. It's a product, x times y squared. So I'm going to write this as the log of x plus the log of y squared. The log of a product equals the sum of the logs. Not the final answer. Log of x is done. We can't do any more with that, but we can do a little bit more with the log of y squared. Y squared is a single expression raised to a power. And when we have that, that power can come out in front. So this is going to be the log of x plus 2 times the log of y. And now it's done. That's completely expanded, and we've written it in terms of the log of x and the log of y. Now suppose y, we don't know it, but later find out that y is a negative number. What would be the issue with this if y...
It's not equal, higher, positive. No.
Well, suppose y is negative. If y is negative, could we take the log of y squared? If y is negative, what can we say about y squared? It'd be positive, so the log of y squared would be okay. But what about the log of y? It would not be okay. So we've got issues. We're saying log of y squared, which would be some real number, is equal to the 2 log y, which would be some imaginary number. That's a problem. So what we'd have to do is observe that the log of y squared is equal to the log of the absolute value of y squared. How do you feel about that? Is the square of any number equal to the square of its absolute value? Pick a number, any number. Maybe you want to make it a real number. Pick a real number, any real number. 6, okay. 6 squared is 36. Take the absolute value of 6 and then square that. Do you still get 36? Sure. What if we take a negative number like negative 5? If you square negative 5, you get 25. What if you take the absolute value of negative 5 and then square it? You get 25? Sure. So the square of the absolute value is the same as the square of the number. So then you take the 2 out in front, and it would look like that. Now, I'm not going to stress you out any more than absolutely necessary. And this I don't think is absolutely necessary because we're assuming all variables are positive. But if we didn't, a consideration that would have to be made is this. You'd have to enclose the y in absolute value bars. Okay. Don't worry about it. It's not going to come up. But that's why we assume all the variables are positive for simplicity there. The D part, log of a quotient, x cubed over y square root of z. So log of a quotient is equal to the difference of the logs. So it's the log of the numerator minus the log of the denominator. Log of x cubed minus the log of y times the square root of z. Now, at some point I've got to deal with that square root of z, but maybe not just yet. What can be done with the log of x cubed? 3 log x. So that 3 comes out in front, and it's going to be 3 log x. Now, really dangerous thing here, because I've got that minus, which means I'm subtracting the totality of this expression, whatever that expression ends up being. And as long as it's just a single logarithm, there's no need for parentheses around that logarithm to indicate we're subtracting that entire quantity. But when we take that logarithm and expand it, we're going to have to write it as the sum of 2 logarithms. Somehow we have to indicate that we're subtracting that entire sum. So where there were not previously parentheses, we're going to need parentheses, just like that. or we're going to miss the sign in front of the log of the square root of z. So it's minus all of this, and all of this would be the log of y plus the log of the square root of z. Now I want to do two things at once. I want to clear the parentheses and also rewrite the square root of z. We don't have a nice property of logarithms that tells us what to do with the log of a radical, but we do have a nice property of logarithms that tells us what to do with the log of an expression raised to a power. So let's take the square root of z and write it as z raised to the power of 1/2. 1/2? Z to the 1/2. So let's do this. 3 log x minus log y. Going to go ahead and distribute that minus across the parentheses. Minus log z to the 1/2. So two things at once. Clear the parentheses by distributing the negative across and replace the square root of z by z to the 1/2. Kind of independent of each other, so I think I can get by with doing both those things at once. Almost done. What's the only little thing that has to be done? Put the 1/2 in front of log z. So 3 log x minus log y minus 1/2 log z. Some observations. In this expression, x cubed is in the numerator. That ends up being a positive 3 log x. Y is in the denominator. That ends up being minus log y. And the square root of z is also in the denominator. That ends up being minus 1/2 log z. So if all the exponents in the original expression are positive, those expressions in the numerator end up with a positive coefficient. Those logarithms do. And the expressions in the denominator end up being arguments of logs with negative coefficients. Now, if a mixture of positive and negative exponents in the original, then all bets are off. But if they're all positive in the original, being in the numerator is going to lead to positive coefficients. Being in the denominator is going to turn those exponents into negative coefficients. Same thing here. They're both in the numerator. There really wasn't a denominator, so they both ended up being positive coefficients. Is it time to reverse the procedure? Yes, it is. Example 3. Write each expression as a single logarithm with a coefficient of 1. Assume all variables have values that make all arguments positive. I don't think argument needs that e there. I think it's okay without the e. Assume all variables have values that make all arguments positive. So while I'm making more space in my notes, I can maybe check my spelling as well. All right. Condense the logarithms. That's what we're doing here. So we'll start with the multiple logarithms on the right and try to squish them in together into individual logarithms on the left. So we're thinking sum of the logs equals the log of a product, difference of the logs equals the log of a quotient. We'll start off, though, with a number times the logarithm. These coefficients are going to turn into what? Exponents. 2 log base 3 of x is going to be log base 3 of x squared. And 1/2 log base 3 of y is going to turn into log base 3 of y to the 1/2. Eventually, I think my math lab is pretty particular about that. It would prefer not to have fractional exponents. It would rather have the radicals in the final answer. So we'll convert that to the square root of y. Minus log base 3 of z to the 4th power. So I'm thinking of this as subtracting positive 4 log base 3 of z, so I keep the minus, and I take the positive 4 and make that the exponent. Not a bad idea to stay away from negative exponents, if you can. Once we get to this point, and we're condensing the logarithms, and they all have coefficients of 1 or negative 1 if there's a minus in front of the term, let's follow order of operations which say do addition and subtraction in order from left to right. So if we have a log plus a log to start off with, we'll take these two logarithms and condense them into the log of the product of that expression. So the x squared gets multiplied by y to the 1/2, maybe just to be on the safe side. I could save it to the very end, but let me just copy and paste everything and go ahead and call that the square root of y. Nothing else changes, just calling that the square root of y. So I don't forget to do it at the end or run out of room. Now I'll condense the two logarithms. The log of x squared plus the log of the square root of y is the log of the product, x squared times the square root of y. And incidentally, it's best not to think of that as factoring out the log, or however you might think of it, how it might resemble something else that you've done. Because if you think of it like that, you're going to end up putting a plus in between the x squared and the square root of y, and that's just not quite the same thing. Difference of the logs is the log of the quotient. We're subtracting logarithms, so we're dividing the arguments of those logarithms. So log base 3 of x squared times the square root of y over z to the 4th. And once we have a single logarithm with a coefficient of 1, that one's done. So observations. The 2 log base 3 of x, the x squared wound up as a factor of the numerator. Positive 1/2 log base 3 of y, square root of y wound up as a factor of the numerator. And negative 4 log base 3 of z, z to the 4th, wound up as a factor of the denominator. Next one might be a little bit on the trickier side because there's a minus in front of the first two instead of a plus, but we'll cross that bridge when we get to it. The 3, the 1/3 become exponents first of all. Natural log of x cubed minus the natural log of x plus 4 to the 1/3 power plus the natural log of x squared plus 6. Nothing going to happen much to the natural log of x squared plus 6 for a while. There's really nothing we can do with it until we can combine that x squared plus 6 with another argument. Like I did at this step in the previous one, let's take the x plus 4 to the 1/3 and go ahead and write that as the cube root of x plus 4. Now, if you wanted to rearrange the terms, rearrange the logarithms so you had all the pluses in front and all the minuses at the end, it would be okay. You could say this is equal to the natural log of x cubed plus the natural log of x squared plus 6 minus the natural log of the cube root of x plus 3 on the x plus 4 on the end, and just see how that works out for you. It probably would be simpler, and you might avoid a common careless mistake. But I'm going to try to attack this by doing the subtraction first. Difference of the logs is the log of the quotient. So this is going to be the natural log of x cubed over the cube root of x plus 4 plus the natural log of x squared plus 6. One more step, which might end up being 2 more steps. The sum of the logs is the log of the product. So somehow, some way, we have to multiply x cubed over the cube root of x plus 4 by x squared plus 6. It needs to look like this. X cubed over the cube root of x plus 4 times, and a lot of times it's easier, maybe for me, maybe for everyone, to think of it as multiplying by a fraction than it is by multiplying by a polynomial, because we can remember the rules for multiplying fractions because they're so nice. Just multiply the numerators, multiply the denominators. So if we write it like this, I think it's easier to remember what we're supposed to do. We're supposed to multiply the numerators, x cubed times the quantity x squared plus 6, And we're supposed to multiply the denominators, the cube root of x plus 4 times 1. And then it's done. Single logarithm with a coefficient of 1. Positive 3 natural log of x. X cubed ends up as a factor of the numerator. Positive log of x squared plus 6. X squared plus 6 ends up as a factor of the numerator. And negative coefficient on the natural log of x plus 4, cube root of x plus 4, ends up as a factor of the denominator.
So your final answer is that.
So this is the final answer.
Yeah.
To multiply out the x cubed times x squared, it's probably better to leave it in factored form like this. That way, if we had to turn around and expand it, we wouldn't have to factor it first in order to do that. So there's no e part, but suppose there was, and it said example 3e, natural log, actually 2 times the natural log of x minus 1/2 times the natural log of y plus 5 times the natural log of z minus 1/3 times the natural log of w. If you want to condense that into a single logarithm with a coefficient of 1 and not show any work, just write the final answer. One step.
What's the last letter?
W?
Oh, it's a W.
Yeah, W. What is the final answer? Natural log of what? X squared?
1 or 5. Square root of that.
Z to the 5th?
Square root of log.
Just like that. I'll reverse the process. If this had been example 2e, we take something like this and expand it, which is more common maybe in a calculus course where you're trying to find the derivative of some complicated expression. If you have the natural log of what might it look like? X cubed times the square root of x squared plus 5 over x plus 14 quantity to the 7th. Can you completely expand that in one step? Oh, I think you can too. What's the first number I write down?
3.
Well, 3 right in front of the natural log. 3 natural log of what? Of x. Plus or minus? Let's do the plus first. Plus 1/2. Natural log of
X squared plus 5.
x squared plus 5 minus
X
7 times the natural log of x plus 14. Turns out that these expressions, x squared plus 5, and x plus 14, a lot easier to manage than this great big complicated looking quotient with a lot of stuff going on there. So we can exploit these properties of logarithms, make the expressions easier to deal with in some cases. And then there's the change of base rule. Change of base rule. if we need to evaluate the logarithm of some off-the-wall base. By off-the-wall, I mean anything other than 10 or the natural base e, can do so on the calculator, even if it's not one of the brand spanking new TI-84 pluses. With, I think there's a log base feature, but a student asked me how to use it last night, and I really wasn't sure because I don't have one of those on my calculator. You take the log of the argument and divide by the log of the base. That's just what you do. So if you want to find log base 4 of 8,192, let's get this calculator fired up. You take the log, pick a log. You can use the log log, base 10, or you can use the natural log, ln. At some point, I mixed and matched the logarithms and made a mistake, but we were doing this in last night's class. You don't want to do that. You want to be consistent and use the same type of log. So I guess what I should do is copy that and then paste it with maybe the calculator description. That would probably be most helpful. So let's see if I can find log base 4 of 8,192. What you do is take the log of 8,192, using the base 10 log there, and divide that by the base 10 log of 4, and it gives us 6.5. This is the power that 4 can be raised to. To get 8,192 is the answer, just to check it. If we take 4 and raise it to the power of 6.5, we get 8,192. So let me take a picture of that. Put it right there. If the log button is broken, but the ln button is functioning properly, you could use that instead. You could say natural log of 8,192 and divide that by the natural log of 4. Now it should be noted that the natural log of 8,192 is not the same as the base 10 log. It takes a much higher power to raise e2 to get 8,192 than it does to raise 10 to get there, but the ratio is the same, 6.5. So either one of these accomplishes the same result. Pick either one of these logs, take the log of the argument, divide it by the log of the base, and you get the value of that off-the-wall base logarithm. You can use this if you want to sketch the graph using your calculator of a logarithm to one of these off-the-wall bases. For example, suppose we wanted to compare the graphs of y equals 2 to the x and y equals log base 2 of x. Well, on your calculator, you can just type in y1 equals 2 to the power of x, but for log base 2 of x, you need to use the change of base formula. y2 equals the log, and I'm going to go with the base 10 log of x divided by the log of 2. So let's see what that looks like. It's going to be 2 to the power of x, and then log of x divided by the log of 2. One more thing, let's do the y equals x, because these two are going to be symmetric to each other about the line y equals x. And I'm going to zoom 6, and I'm going to follow that up with a zoom 5. Zoom 6 so we get a standard viewing window, and then zoom 5 to make it a square viewing window. So zoom 6, there's y equals 2 to the x, and then there is the inverse, y equals log base 2 of x, and I don't know if they look quite, in fact they don't look quite symmetric about that line, maybe close, but not exactly. If we zoom 5, what it'll do is adjust, I believe it adjusts the x min and the x max, expands them a little bit so that it'll be more of a square viewing window. So that the distance between consecutive tick marks on the x-axis is exactly the same as distance between consecutive tick marks on the y-axis. And there you see the symmetry.